Hi, good morning, and welcome to the ZP Developer Zone and webinar. So we like to do this once a week, and it's basically answering questions or technical questions, sometimes with a slight commercial bent that have come in during the week. But let me jump straight into it and be respectful of the time. So we do have the ZP Academy. This is a website where you can sign up for a couple of free courses. We do have these webinars. This is an example of one of those kind of webinars where we will answer technical questions for the week. We do have collaborations. These are primarily in the UK and Norway, where the funding is kind of essentially in place. We have something like 5 PhDs running at the moment, at least in the UK, and then more in Norway. We do have jobs, and we do have the Developer Zone website, and we do have workshops. Workshops, not something I'm going to talk about so much today, but we do hold monthly in-person workshops, both around IVD and also around wearable sensors as well. But let me go a little bit faster and say the whole philosophy at ZP, and this will pop up a little bit today, is really about solving real world problems, whether it's nitrate in the soil, maybe it's potassium in the blood, or maybe it's glucose in the blood. And then there are people who want to provide solutions to those problems. So for example, academics, entrepreneurs, businesses. And then what we try to do at ZP is essentially provide the technology between the problems that people have and the solutions that people would like to provide. So for example, something I'll talk about a lot today is our Sensi-All platform. So the Sensi-All platform, if somebody's doing the detection of heavy metals, then the Sensi-All platform will allow them to translate that lab work into an actual tangible product that can actually get sold. If somebody's interested in measuring things like glucose, potassium, sodium, pH, lactate, oxygen in the blood, then the Sensi-All platform is a way of translating that. If somebody's interested in measuring hormones in a continuous manner, then the Sensi-All platform is the platform for that. The Sensi-All platform, though, has a very good hardware technology and a commercial, what's called a drop ship model built into it. It does, there's still some work to be done, so it does require some funding from you. So this is Sensi-All. Anyway, this really summarizes the whole philosophy at ZP, which is get technologies into people's hands as quickly as possible, start collecting data, and then start actually iterating to improve how the system actually performs in that real world. Too much time is spent building hardware, building sensors, building electronics, and then people find out that actually what they have is not really what the end user really wants. The philosophy I'm kind of, or the strategy I'm discussing here is something that's called kind of really from a lean startup strategy. But you don't have to be a startup in order to be using this lean philosophy. Lean is also now used in quite large organizations as well. It just means doing things quickly and getting to an MVP and minimally viable product really quite sharpish. We do have a couple of webinars in January, one on Sensi-All. So if a lot of this resonates with you today, please sign up for this webinar. I'll make sure I put the link underneath the video as well. And we also have our Food Sense webinar. Food Sense is a reflection on this. A lot of what we're trying to do at ZP is take electrochemical sensors and put them in the real world. And so we're doing that for testing the quality in food ingredients. So we're measuring, it sounds quite funny, but we're measuring the hotness of chilies, the pungency of ginger, and also something called TAS, total antioxidative status, which is a predictor of shelf life. We are having a conference in the UK in June this year. I'll put a link to it as well, and it's really about the commercialization of electrochemical assays, which is really kind of at the heart of what we like to do here at ZP. So to the questions, there's 5 questions. There's quite a lot to get covered. I'm going to speak fast. Question number 1, somebody's doing the anodic stripping voltammetry, or the analysis of heavy metals, and they've been testing copper, cadmium, and zinc, and they have some unusual signals, let's say, for copper. And I think it really comes down to the ammonium acetate that they're using, but I will discuss that in detail. Somebody else, they really just want to know if what they're trying to do is feasible. Things are feasible, but you do have to ask yourself, but what's I think a little bit different about ZP is, even though things are feasible, you go to an engineering firm and say, can you do this? The answer is, yeah, we can do it. The question you've got to ask yourself is, can you really do it at scale? Can you manufacture it at a low cost? and what's really going to be the quality when actually you don't have large volumes of manufacturing. So these will be the points that I cover. This will also, question number 2 is really related to question number 5 as well, where somebody else is looking for what we call a custom screen printed electrode. So the question to 2 and 5 just referred to, look at the answer to both. When I answered both these questions today, go back and find the answer. If you're number 5, look at question 2, and if you're 2, look at 5. Question number 3 is an interesting one. This one's really for measuring. They came in and asking about measuring of cortisol. I feel like the question is really, can you measure cortisol continuously in a wearable sensor? And I'll answer that. I suppose I haven't answered it to a lot of work that we have done a lot of cortisol work. We've also looked at things like testosterone in saliva as well. I haven't brought that up in the slides today, but that's something we have done as well. Description, question number 4 is, can we measure glucose, lactate, sodium, potassium, oxygen, and pH? Quick answer, of course, is we can. Can we measure them in media? In what media can we measure them? Well, so in the end, this is electrochemistry. So electrochemistry, obviously, if you think about glucose, then the biggest biosensor in the world is the glucose strip. All glucose strips work in whole blood, and they happen to be electrochemicals. So electrochemistry is really good for samples. So the sort of samples that we talked about here are blood, interstitial fluid. That's something that we do quite a bit at ZP. Urine, we've always got sensors going into urine. Saliva, I mentioned testosterone detection earlier on in saliva, and we also work with things like tear film as well. So at ZP, we seem to we do specialize really in measuring things in the liquid phase. What that liquid phase is, we're less sensitive to. So for example, come to our Food Sense webinar in January, and you'll see us measure capsaicin in chili sauces, or you'll see us measure gingerol in ginger shots. These are quite dirty, very opaque, full of floating materials. You know, they're not super clean samples. So electrochemistry is quite good for less than ideal samples. I think it's one of the best sciences for that, actually. Question number 5, they want to make a screen printed electrodes. I've always got a comment on platinum and gold these days are super expensive. If you can ever develop not using platinum and gold, you are doing yourself a massive favor. And also, when you're thinking about having a custom screen printed electrode, try and make it as small as possible. Now, I understand these people are trying to make a microfluidic device, and the reason that's significant is because they want to use essentially what we manufacture as the substrate for the microfluidic device. But you might have to think about having a base for your microfluidic device and essentially the screen printed part being an insert into it. Otherwise, you're loading up a lot of cost on that screen printed electrode part, and you're not going to be happy with the cost. Let me go forward a little bit faster and say, that why many people come to us at ZP is because we do have quite a portfolio of electrochemical sensors. And I realize the list is even sort of getting longer these days. Just out of interest, a lot of the electrochemical sensors that I'll talk about today are if it's what I would call our IVD sensors, in vitro diagnostics, then they're 25 millimeters long, 7 millimeters wide, just FYI. We do a lot of screen printed electrodes. These are our kind of our top selling screen printed electrodes, and because they're top selling, it means we manufacture them in the highest volumes. And if you want something to be low cost and high quality, a good start is to be manufacturing quite high volume. Everyone thinks about screen printed electrodes and thinks, oh, they're low cost. Well, the low cost means that they're probably coming out at low quality, and if we want to keep the quality high, then we have to manufacture quite a lot of them. So these are the guys that are kind of our go-to sensors at ZP. I suppose I should say that ZP, the biggest consumer of ZP electrodes, is actually ZP, and that's a good thing, because what it means is we keep the quality high because we need to benefit from it directly. And then, by the way, we also sell these screen printed electrodes to the R&D community through our websites as well. By the way, if any links are popping up today, I will add the links underneath the videos as well. Let me go a little bit faster and say that we do have this Sensi All platform. Sensi All platform is part of this philosophy of sort of lean, and lean by lean, I just mean let's get these technologies, these products into people's hands. And when I mean people, real users, as quickly as possible. Let's not spend years developing and then find out it's not actually what people want. That's, it's a bit of a shame when that happens. Actually, people can spend good 15 years doing work, let's say, and it, in the end, it's not actually useful to society, and that's a little bit of a shame. The two things I will talk about today really is what I call our electrochemical platform, though we do have a spectrochemical platform as well, and I will also talk about our wearables platform, which is also electrochemical as well. So I think the one in the middle really talks about what I call sort of point of need testing. Sometimes it's called point of care diagnostics if it's specifically in the medical field. Sometimes people call it spot testing. I have a sample, I put it on the center, I get a result. The one to the right, the watch format, is actually more for wearables. So the biggest wearable biosensor in the world at the moment is the CGM, the continuous glucose monitor. Everyone's very familiar with these, is becoming very familiar when people have got these little discs on the back of their arms. That's the CGM. And there are some of the companies now working quite hard to get those technologies out of diabetes and even into wellness monitoring as well. So they're becoming quite familiar to people. I'll talk about that a bit today. Question number one, though, is about some copper data. So somebody's doing some anodic stripping voltammetry. Anodic stripping voltammetry is a good way of being able to detect heavy metals, A, detect them, and B, quantify them in samples such as water, which is quite nice because people are quite interested in if it's mining tailings. So mines, people have been mining materials leaching into the local rivers. Then you can detect the heavy metals. You can detect the heavy metals sometimes in pumped water. The deeper these mines, these pumps go sometimes for water sources, then the more likely they are to have heavy metal, especially arsenic, unfortunately. So people are very interested in measuring heavy metals in water. These particular inquirers, I believe they're using the hypervalue carbon electrode. It's a good choice. It comes back to my earlier statements that at ZP, the reason that we're able to get kind of quality into our screen printed electrodes is because A, we're the biggest users of them, and B, because we're using them a lot and we're selling them, then we're actually able to get them at high volume. I will talk about how we're also doing all this testing of these electrodes before they actually ship, and that actually ensures the quality. We do have a nice 501 electrode that's come along as well. I think especially for academia, academics like to kind of pipette when they're functionalizing electrodes. They're always asked us for these circular electrodes, so we've also now brought about this circular electrode design as well. So they sent me the data, it's nice data. They're quite happy with the cadmium and the zinc, but they're concerned about the copper data, so I will comment on the copper data now. Just to say, I do have some resources around the detection of heavy metals and platinum group metals. I have it on the website. If you see a link pop up, then I'll make sure I put the link underneath the video as well. So looking at their data, their kind of concern is, well, they've got a concern that they've got multiple peaks. I'm not concerned by this. I'll try and explain at least some explanation. But then they're concerned that they're looking at this biggest peak and they find out that they've got some concentrations here in ppm, so 9 ppm up to 33 ppm. But their concern is that this is the 9 ppm and this is the 33 ppm. So I understand their concern there because they want the peak height or the area under the curve to be proportional to the concentration, which they've measured in parts per million, and it's not. Now, ZP, we are, a business model is primarily contract development, contract manufacturing. So in this case, we're often, we want to go to a quantifiable sensor as quickly as possible. So when I look at their data, I actually see that there are peaks in their data that are proportional to copper. So as a pragmatist, I'd actually be, I'd have our team focusing on the peaks at 25 millivolts because I know that it's easy for us to write an algorithm, apply it to our Sensi-All platform and say, okay, you have a sensor. The algorithm would look for the peak at 25 millivolts. That is linear with concentration. We would use that. But you may want to know what's happening in your system. So I am going to try and at least give you some opinions on what's happening in your system. So as I say, this is the 9 ppm data. This is the 33 ppm data. This is the 28 ppm data. This is the 23 ppm data. And this is the 16 ppm data. So I do recognize that you don't have, in this particular peak, linearity with concentration. But as I say, if I look at this peak, then your lowest concentration, 9 ppm, is here. Your second highest concentration is here. Your third highest concentration is here. Your fourth highest concentration is here. And your fifth highest concentration is here. Boom. Therefore, I'm therefore happy. So as an industrial, I would say, electrochemist, then, and I want to most of the time people are very interested in, time to market is everything. So if we can just use the first peak in order to quantify copper, we will. It is easy to do this kind of work. So for example, we have a system called Sense It All the data goes to the cloud. In the clouds, Julie, which is a database we have, is able to say, we're able to say to Julie, find the first peak, find the area under the curve, use a calibration factor to then turn that area under the curve into concentration, and we're done basically. But I do understand that you want to understand a little bit more about what's actually happening here, so I will. I'll give you my pragmatic opinion, but now I'll also dig into it a little bit more. It's interesting to see because this relationship between lowest to highest concentration is also preserved in peak 2. So peak 1 and peak 2 are telling me that signal is versus copper concentration. When we go to peak 3, I should label these up as peak 3, but I'll call this peak 3 here. Highest is highest concentration and lowest concentration is lowest signal, but in the middle it gets a little bit more mixed up. And then, as I say, when we go to peak 4, which is this last one at about 100 millivolts, that's when it does break down. So I've kind of just labeled it up here. I said that peak actually works, that peak works, that peak starts to get a bit borderline, and that peak doesn't work. So I think what you're having here is you're actually oxidizing copper in essentially 4 events. And it works well on the first event, works okay on the second event, starts to break down on the third event, and doesn't work on the fourth event. Because you've basically depleted the copper in the first 2 peaks. So it's sort of this relationship between copper concentration and copper peak has really broken down, because the simple model which says you plated it and then you oxidized it is not true here, because you're actually oxidized it first, second, third, and fourth. I will explain to you what I think is going on here, and the clue is in your email, which you said we're using ammonium acetate. I got a suspicion that is the clue to this. I suppose this is quite nice because in fact we've done our own work on here. We're doing the analysis of lead and copper. We have a nice clean copper peak, and we don't have peaks either above it or below it the same way that you're reporting. So and in this case we're using something that's much more native. I say here sort of when I say native water, I think it's more like tap water. So we're definitely not adding ammonium acetate, which I think is your material. This is just a side note really, that anodic stripping voltammetry, what's happening in anodic stripping voltammetry is they have some copper. They're applying a negative potential. They're depositing the copper onto the electrode, and then they strip the copper back off again. And that works quite well when you've got a simple, can I say, 2-step process. One step you deposit, and another step you oxidize. And that works quite well for them as long as they're looking at what I labeled peak 1. By the time they get to peak 4, that simple relationship is broken down because they've already done 3 oxidations before they do peak 4. So I'm not super shocked that peak 4 is actually not, and is no longer linear. Because you've got an oxidation here, an oxidation here, an oxidation here, an oxidation here. So by the time you get to looking for a relationship in oxidation 4, where you said, right, well, that peak should be proportional to the original concentration, the simple relationship's not there because you've had at least 3 oxidations on the way to get to that 4th oxidation. Question is, why is it happening? And it's because I think you're in ammonium acetate. We're not in ammonium acetate. See, so the big difference between you and us is we're both using the same screen printed electrode. We're both using anodic stripping voltammetry, except you have these peaks and we don't have these peaks. So I think ammonium acetate might be the clue. I don't know if you're oxidizing copper to copper 1 here, maybe copper to copper 2 here, but that is one of the things about copper. It does have a couple of oxidation states, whereas cadmium and zinc actually just have, I think it's just a +2 oxidation state, if I remember rightly. So that's the first thing. That can be your complexity, but I think your complexity comes about because copper can actually have lots of coordination chemistry. And I just did a quick search on ammonia complexes of copper, and I kind of, God, it's been such a long time. This is tetrahedral, this is octahedral. I forget what this guy is and this guy is. But that said, you've probably oxidizing copper, but releasing different complexes, and that's because you're using ammonium, which is a source of ammonia, and therefore forming these complexes. In our solutions, which I think was much simpler, you didn't have that capability of forming these complexes. It's actually, to really know what's going on, by the way, I'd actually say that, you know, it'd almost take a master's project to do a whole series of experiments where you were adding things, taking things away. When I say adding things, you sort of try and experiment with ammonium acetate, without ammonium acetate, and you start to understand whether these peaks are linked to ammonium acetate. But you have to do it in quite a systematic way. But as I say, we don't, the big difference between what we've done and what you've done is actually, I think, that ammonium acetate. I suspect that at least is it's at least a rational reason as to why you get these extra oxidation peaks. Just a side note, not to these guys, but to people in general, that we've also done a lot of work with lead. Lead is also heavy metal. And what we can do with the Sensi Ore platform is, if people want to really develop a technology for end users, things like the hyper-value electrodes, the Sensi Ore platform. We have a Sensi Ore app that you will see as part of this webinar today. We also have a system called Julie. The app will tell the hardware what to do. So these people have developed an assay for copper, cadmium, and zinc. So the app can be trained or told to run their assay. They can put the electrode in there. They can put the sample on there. The assay will be run by the app. The hardware will give the data back to the app. The app will pass it up to Julie, and then they'll actually get a concentration of like ppm, for example. And then actually they also get hold of the raw data, because Julie's is actually a data management system, and they can actually make, they can either look at the data themselves. They don't have to show the raw data to the end user, by the way, because end users are not interested in electrochemical data. They just want results. I should have labeled it up here, but Julie has also an API system on it, an application program interface as well, that allows people to pull data across the third-party databases. We are doing a webinar on Sensi Ore in January, so it's probably worth attending that just to kind of get a sense of the Sensi Ore platform. And it's really developed with the idea that actually somebody's doing some lab work and they want to translate it into a real product, and Sensi Ore can just do it really easily. Just a quick comment as well, actually, this will come up later on, but the Sensi Ore, for a product to be for a product to really kind of make sense, especially in this kind of point of care testing, you have to kind of get to fairly high volumes. You know, so for example, high volume is not really selling 10,000 units, but if people are able to send 10,000 units, then the Sensi Ore platform is actually €60. But to get that really low cost, you do need to be selling things like 10,000 units. So that's quite hard to build up that kind of pipeline. Question number 2 is about custom electrode systems. So at ZP, we do make a lot of screen-printed electrodes. These again are sort of the ones that I tend to focus on a lot, and we use them a lot in our own lab. This one is carbon, this one is platinum, this one is carbon, this one's platinum, and this one is gold. These are the links to all of those. Nothing more to really be said about it. They've got a description. So I've read the description, and I sort of translating the description into, they have a well that's about 16 millimeters across. And they want to make an electrode assembly, which is 2 gold electrodes, which have an area of about 1 millimeter to 4 millimeters squared. An electrode that is, I think it can either be platinum or gold, but it's 40 millimeters squared, so that's significant because it's quite big. And they want to have a platinum electrode. I'm a little bit confused by this point, which is they want to then attach it to, I feel like, some sort of isolated silver chloride electrodes. The thing about this is, I mean, you can do this kind of stuff. I mean, and you know, it's they also are interesting, can they make an edge connector and can they do it through the lid? Yeah, all this can happen. I mean, it's just not just, it's an engineering task. You know, for us, if we would start with a sketch, and from a sketch we could produce drawings, and from drawings we can produce the device itself. So it is feasible. You just got to kind of, people jump too quickly into doing it. ZP would actually want to be on a bit more of a paid consultancy on this, because it really has to be thought through. Is this really the best way to go? So in the answer to the question, is feasible. Would I just jump in straight into it? No. I probably purchased a couple of hours of ZP's consulting to really talk through this. I'll give you some of my thoughts or concerns here, and then they want to put that through into the well and make some sort of edge connector on the outside, which is fine. I say here, please send me a sketch. Well, a sketch will be helpful, but a sketch we'll have to have a discussion on it. I say here 2 problems. I should have actually labeled this as 3 problems. Reproducibility. When you have something custom made, especially screen printing, there's plenty of businesses around that will actually, so yeah, they'll screen print for you. But what they won't talk about then is reproducibility. That actually, when you do low volume custom screen printing work, it's not necessarily reproducible. The object that you're describing is quite large, and it has platinum on it and gold. Platinum and gold are expensive materials, so the materials themselves are going to give you a cost, and then the size of the device as well. So I will talk about a term that's not used very much, but I would call it manufacturing density. How many devices can I make per second? And because the larger you make this device, then the less devices we can make per second, essentially. And then really quality, and quality does come from reproducibility. And if you don't invest in it, you know, people will just screen print you something, ship it to you, it looks great, and then it's not reproducible. And that's the biggest kind of quality concern I have on this kind of device. When it comes to reproducibility, come to a couple of our webinars. On food sensors is a good one. There is a link. I'll put the link underneath the video at the beginning of this. But when I talk about reproducibility, what you'll see is when we do our kind of work, we never do calibration. So ZP, I mentioned this term lean startup. Embedded in that kind of lean startup philosophy is also that the technologies that we have coming out of the work that we do for ourselves or do with clients is it's not calibrated. Whenever you have to bring calibration to a sensor, it's not easy to use. It doesn't give a good user experience. So the fact that we have no calibration is really because of the reproducibility either of our sensors when we're working with clients that are actually going to market, or with the reproducibility of our screen printed electrodes. And the 5 that I've linked up above are pretty good because we use them a lot. We do something called wafer mapping. I think I'm the only person who uses this term because I've spent some time in the electronics industry. But wafer mapping kind of says, here's 300 electrodes in a sheet, and we'll test them by voltammetry to make sure that they're reproducible. So example, we would reject this sheet, but we would accept this sheet, and we would accept this sheet, and we would accept this sheet, and we would produce something called KPIs, key performance indicators. We would test a number of sensors on a sheet. Then we would look at the mean of that, look at the standard deviation of that, look at the relative standard deviation of that, and actually then pass these sheets and make sure that if the sheets pass, then we'll pass the batch. And by the way, we do reject batches. You know, we are ISO 13485, so we are qualified to do the development and manufacture of medical devices. We use our own screen printed electrodes in our own products, so we're really cautious about this. We do actually reject materials as well by going through this process. So the first person to know whether something's working or not is actually ZP, because we'll spot it before it actually gets shipped. So that means then that we don't need calibration, because if we were doing a concentration versus signal versus concentration graph, we would find that we actually had good repeatability at each concentration, and therefore we don't need to do in-field calibration. Whenever you do in-field calibration, or people are often normalizing data, what they're really trying to forgive is that they've got manufacturing issues, and they're kind of basically carrying those issues into the field and making the end user do some sort of calibration to kind of offset that. That said, I just want to comment on gold and platinum. This is also in reference to question number 5, who's also asking for, I think it's a platinum electrode as well. I do focus here on gold, just out of interest. Our gold electrodes are really good. We do use them a lot in aptamer work. So if somebody's come to us with a hormone, we might end up using an aptamer or an antibody. And we often use the technique of EIS. I do cover this quite a bit in some of our workshops as well. But we do use gold electrodes quite a bit in these kind of immunosensor type assays. So my problem I've got with gold is it just is getting so expensive. So at the moment, gold is about $71 per gram. Printing with gold and platinum is actually really expensive. I think, and most assays, if you really think them through, you can actually make them work on carbon. If you work on carbon, if your ultimate goal is to make a low cost, scalable help real people in the real world product, then you really have to think about engineering gold and platinum out of your product and actually stick with carbon. Carbon is like 1/28,000th of the cost of gold and platinum. So I really would think about engineering. I've also got a bit of an issue with, I would say, probably with platinum as well as gold and platinum actually, is that the places it's mined in the world, it is causing a sort of an environmental pollution concern for me. So pulling gold out of the ground is really quite a polluting thing. So I don't consider it particularly sustainable, let's say. And if you ever if you just Google a gold mine online, you'll soon find that they're kind of like large scars in the ground. Then there's a local pollution problem. I don't think they're particularly sustainable. They're not always coming from, well, they come from various places around the world, and you've got to look into the sort of the politics of these places where the gold is sometimes coming from. Just out of interest, one of my concerns with the product that's being asked for here is possibly its size. It sounds like it's getting quite big. And when I say manufacturing density, in this sheet, for example, we are able to place we're able to make 300 electrodes at a time, so our manufacturing throughput's quite high. Once you start making a much larger object, then the number of, say, electrode arrays per sheet decreases, and you're basically going to be paying for that, because the more we can make per second, then the lower the overall cost per electrode array actually is. So I've got a concern with your size. So I've got a concern, I say here 2 problems. I actually thought of a third problem, which is the quality, but reproducibility, which effectively does come down to quality, cost, which is also linked to your size and choice of materials, and then I think quality as well, that you've got to understand that there are plenty of people who will screen print this kind of material for you. But because it's a bespoke, often just a one-off effort, even if you want to say, oh, I'm going to make thousands a year or millions a year, in the early days it's still manufacturing is not something that just comes about straight away. It has to actually mature. So I think you really will suffer from quality on this. But send me a sketch, and that will be the next step if you want to work with ZP. Hormones, somebody contacted us specifically about cortisol. I will talk about, this will make you smile, cortisol, embedded cortisol sensors in fish. But I did ask them a question, what other hormones are they interested in? And they mentioned adrenaline, oxytocin, vasopressin, beta endorphins, neuropeptide Y, and a couple of endocannabinoids, AEA and 2-AG. I found this quite interesting actually, because when I think about hormones, I kind of think about estrogen, I think about testosterone, I do think about cortisol, so some of these were kind of interesting to me. We do have these platforms, so we actually do, in fact we're doing it at the moment, we're doing some testosterone work on the central platform here, on this electrochemical platform here, and we also have a wearable platform. We also have, I'll talk about our cortisol work as well, but the one thing I should say is that at the moment, the only animal that is benefiting from at least our cortisol sensor of fish. Sounds crazy, but I'll give you a bit of background on that as well. So we do have a whole bunch of electrochemical sensors. If anyone's interested in doing hormone sensing with us, we have the cortisol sensor, which has had a lot of work put into it. Also the testosterone sensor, we do have customers on that. And I have done some work in the past on a hormone that's related to something called bore-taint, which is androstenone. There's also another marker for bore-taint, which is called skatol. Different conversation, not today, but we do have some hormone experience. I did ask them all about the other hormones. One thing I say about adrenaline or epinephrine is it is quite detectable by electrochemistry. In a complex human sample, actually I'd find it harder, but if I was just trying to detect this in a kind of clean buffer system without many interferences, it's actually quite easy to detect. I did look at all the other ones, the oxytocin, I did look at the vasopressin, or this AgCl, it seems to be called, the beta endorphin, and also your neuropeptide Y, and then those endocannabinoids. I should have mentioned actually, we've done CBD and also THC in our time as well, tetrahydrocannabinoid. I forget CBD, but CBD is a very similar structure to THC. But anyway, I did look at these endocannabinoids, AEA and 2-AG. what I would say is the one that's simplest out of all of these to at least do a lab experiment upon is the adrenaline. The other ones, they look like they need an antibody or an aptamer in order to detect them. I haven't looked for where there's an enzyme on them. So I appreciate you telling me, because I just wanted to have a quick look to see if they were fairly straightforward. I'm now going to kind of slightly revert back to the to your real question, which is about cortisol. So I'll jump into it a little bit more. So ZP, just out of interest, we are ISO 13485. We were launched in 2014. We do have a lot of manufacturing and development capability. I have a fairly nice facility with primarily Norway and UK. It says CGM here, but continuous glucose monitoring. If you could do continuous glucose monitoring, then you can also do continuous lactate monitoring or continuous cortisol monitoring. So we're pretty familiar with doing this kind of work. We do what's called planar electrodes, wire electrodes, and also 3D electrodes. And we could do the manufacturing in what's called an aseptic facility. So our facilities are really state-of-the-art. Clean rooms where everyone's gowned up to keep, really, because if you're going to be putting sensors onto people or into people, you've got to really be careful with the not causing infections. So we do have some quite nice facilities. A lot of what we do is a kind of classic wire format. Classic wire format may not so classic to you because you may not be in our field, but this is, if you know, these CGMs, these continuous glucose monitors that people are wearing, these little patches, they're using what's called a transdermal, they call them filament, but you could also call them wire systems. So we're pretty familiar with that. So in fact, we have built this system, or we've built it in two systems, one for glucose and one for cortisol. And so what we're busy doing is, this fish is not dead, by the way. This fish is very much alive. It's just anesthetized, and what we're doing is we're putting this sensing package. You could understand the millions of euros that have gone into this, because making something that's implantable and robust enough to continually measure biomarkers in fish is not that easy. So this fish is actually anesthetized. So that's really, they're basically going to suture it back up. You can almost see the sutures in here already. They're basically going to stitch this guy back up once they've implanted it. And these are fish swimming around with those packages inside them. They're in what's called a RAS system, which is a recirculating aquatic system. So they're literally they call it a racetrack as well. They're pumping the water around, and these fish are swimming around with these packages implanted in them. So we are doing continuous cortisol measurement, but we're doing it in fish. Now we're doing it because in Norway, the second biggest industry after oil and gas is actually is fish farming, and it's salmon. So we're doing it to measure the stress levels in fish. So I would say that what we have today is primarily been using fish. It's not certified and for use for implanting into humans, and we wouldn't, because it's got some batteries in there that we would really have to engineer it out. Too much of a risk. Something that we do a lot of, which is probably more let's say ready for human application, is ZP does a lot of what's called microneedles. We have something like 50 patents on this. So this is a kind of watch format, and on the back of the watch there clips some microneedles. Here's them in their packaging. These microneedles, then we functionalize them to be functional towards the biomarker of interest. A lot of what we do is glucose. We can also do what's called multi-analyte as well. So we can also do, for example, ketones. So ketones and glucose, we've tested them. Make sure the sensors are not cross-sensitive. So we've tested them in solutions of glucose and ketones and made sure that they actually work. That's the one thing about microneedles, is you can do more than one analyte at a time. And as I say, we do this in kind of quite a clean aseptic environments. That's why everyone's wearing these what we call bunny suits. But if I was to summarize it, it's this: that we're not ready to start doing cortisol in a wearable, either microneedle format or a implanted format. We could only really do it as part of a really well-funded program. And if there's not the funding in place, we really sort of can't come involved. Now that can change. So this is, I suppose, if I put a timestamp on this, this is the 17th of December, 2023. So if people are watching this sort of 6 months from now, then that comment, I might have changed that comment. Because the one thing about ZP is we're always improving. at this point, I think the company, you know, we've done 9 years, so you know we're kind of entering our 10th year. So you can appreciate that after 10 years, you know, we get pretty good at getting better. So in summary, we do have a cortisol sensor. It actually is used in fish. If it's more interesting to do hormones in what I call a IVD, a point of care test. So I have done a little bit of work on testosterone, for example, in saliva. So you essentially get some saliva, put it on the sensor, get a result. That is much more achievable. But to make a cortisol sensor that's ready to go on a human being now, that's going to take a lot more funding, and we're not in a position to really get involved unless the funding's in place. Question number 4 is really around what samples can we use our glucose, lactate, sodium, potassium, oxygen, and pH sensors in? So let me have a think about this quick. So glucose, we've definitely done blood. We've even done saliva. Lactate, we have definitely done interstitial fluid. Interstitial fluid is sort of, if you try to do a continuous lactate monitoring, then interstitial fluid is this material that's just immediately underneath the skin. Sodium, we've definitely done sodium in sweat. We've also done sodium in urine. Potassium, we've definitely done potassium in blood. We've also done potassium in interstitial fluid. Oxygen, primarily oxygen in things like cell culture, which is not the same as we tend to. We're not done it on. In one of the easiest ones to do it in is we can probably do it in blood and urine. Well, urine, no sweat. pH. We do actually have something called the calibration-free pH sensor, which might be more interesting. But pH is the most measured chemical parameter in the world. So you can measure pH in cheese, milk, blood. You know, sort of. What I would say about these sensors is they will all work in liquid samples. They love liquid samples. But every time you go to a new liquid, you still have to do development work. So, for example, if you have a glucose sensor, you would have one calibration factor if that glucose sensor was to be used in blood, but you'd have a different calibration factor if that glucose sensor was to be used in sweat or interstitial fluid. So there's always a gap in science. Or there's a gap that always needs filling in. One thing I'd say about ZP is the sensors that we put on our website are really there as a service. They're meant to get somebody from 0 to something really quickly, and they're really intended for R&D purposes only. Oh, I just want to say a good morning to Ali. Nice to see you, Ali. It's been a while, so lovely to see you, Ali. And so what I want to say is that our sensors are very good for using in the liquid phase, but when you have new applications, so for example, it's measuring, if you're measuring nitrate in soil, then you have to have a calibration routine and a sampling routine to get to do that. If it's nitrate in fresh water, that's actually a little bit easier, but still you need a different calibration because it's now a different sample or different matrix. So we have these sensors, but you still have to do some work depending on what the actual application is. So we have glucose, oxygen's on your list, lactate's on your list, sodium is on your list, potassium is on your list, and also pH is on your list as well. So I just want to kind of cover that we actually do have those sensors. Like I say, our philosophy at ZP is if somebody has a challenge, then this Sensi All platform really can be, if you want to measure phosphate in water, let us know, because the Sensi All platform can measure phosphate today. If you want to measure sodium in water, the Sensi All platform can do it. If you want to measure testosterone in saliva, it can do it as well. So we do have this Sensi All platform. So if somebody wants to come to us and start working on, I suppose I didn't mention this, and I should mention it in a minute, that actually all of those analytes that you're interested in can all be run off the same piece of hardware, and I will talk about that in a minute. But it's really important not to spend a lot of time doing the research. You want to get to MVP, minimally viable product, really quickly, get it in the hands of the people, find out what the real problems are. So we definitely work in that kind of philosophy. The nice thing about the platform that we have is it actually automatically connects to the cloud, so you can look at the raw data, and then you can start making algorithm improvements. How do I get that analyte information out of that raw signal with all those interferences going on? But the nice thing about the technology we have is you can put a sample on there. So for example, I've got clients in India at the moment. They're putting samples on sensors. The data is going to the cloud. They choose to share that data with me. I can look at that data, and then we can actually help them understand whether the data is correct or how to even improve it. So that's a lean startup mentality that we kind of have at ZP. If this piece of hardware, it's really quite an elegant, it's much more of an Apple type technology. So anyone who's interested in kind of rolling out sensors into applications, this platform will do it. We can do this platform at 60 euros if we can do orders of like 10,000. So I know 10,000 is a lot, but I just want to give you a sense that actually we are able to really get the cost out. But it's what I was saying earlier on about screen printed electrodes. In order to get cost out, you need volume. So we can get it down to quite low cost. And the whole platform is designed to basically work with apps. The app is called Sense It All. It's already available on the web store. I will talk about that in a minute. The app talks to a cloud system. The customer gets the results there and then, but also the raw data goes up to the cloud, and you can either look at the data with your team, or you can also share the data with a company like us. And it also has API built into it, application program interface. So if your company is all about having a dashboard and giving value to an end user because you're bringing in data, then we can be part of that dashboard as well through the API. By the way, our business model is OEM, which means that we don't want to necessarily go to market ourselves. We want to partner with other people in order for them to go to market. So we do have an API, as I said, built into this as well. Just a couple of videos just to illustrate this. So the hardware is really super elegant. Sensors click in, sensors click out. If for some reason somebody spills something on the particular electrode, one of the things that's wrong with hardware at the moment is people are slotting these kind of sensors into a slot. Slots are horrible. You kind of they're a real problem where you can get liquid ingression and you can really fry the connectors. So we've really thought that through, and we've also got a sort of system level solution as well, which means we have sensors, we have electronics, we have app, we have a cloud system. So we've really taken a systems level approach to it. And the nice thing is, if you've got multi-analytes, that one piece of hardware can actually do all of those analytes. We just use a QR code system. So let's say you were shipping a glucose sensor to somebody. They would get it. They would have, the first time they opened up the app, it would ask them for a QR code. They would scan the QR code and it would say, oh, it's a glucose sensor, and off they go. If later on you wanted to do something like pH, there's actually a pH QR code and a pH sensor as well, so you can just change between quite easily. Now this is recorded, so later on you can get your smartphone out, especially your Android, and scan that QR code, and it will take you to the Google Play Store, and then the app will actually be able to flick between different assays by just scanning different QR codes. So it's a really nice way of distributing new assays out to end users. And as I say, the whole system is actually cloud enabled as well. So the data's not lost to you. The raw data, the entire raw signal ends up in the cloud as well. And you can really analyze that. The other thing about this as well is we've got a business model built into it, a drop shipping business model. So what I mean by that is lots of people are obviously focused on the science and technology, but one day this science and technology actually has to get out into the real world. So we have a business model where it's kind of you have a client and you essentially make a sale. Now that sale becomes instructions. Those instructions come to us. We can manufacture the meter. So for example, we can put them in a box and essentially drop ship it to the actual customer. Now that business model is good because actually to do that, you often need, an accountant. You need some sort of administration. You need somebody to physically put it in the box. This stuff, especially putting stuff in boxes, if I've got tape guns in this office, I tell you, it soon gets out of hand, that you're shipping all the time and going down and shipping stuff. So drop shipping model really allows people to scale. And again, it's part of our lean startup mentality. So even if you're not a startup, businesses these days will have large corporations will have a lean mentality where they want to kind of get market share and get to market as quickly as possible. They don't necessarily want to build up operations at the same time. Last question, because I know we've been going for about an hour now, so my apologies for that. Somebody's interested in a carbon, platinum and silver chloride electrode system. It's probably worth sending a sketch, is my quick answer. One of the things that I don't know why I thought this. I had an instinct that they were making something that was quite large. So it's 40 millimeters by 10 millimeters. As I said, one of a a standard size for us. So these are our top selling screen printed electrodes. I definitely will put a link underneath the video. Something I want to say about them is they're 25 millimeters long and 7 millimeters wide. So you are bigger than us, and that means that your manufacturing density is going to be quite low. I would really think about, don't push on something quite so large, because you're going to end up, if you look at the answer to one of the previous questions in this slide deck today, I might definitely cover the fact that if you can keep things small, then you'll definitely keep the cost down. I also talk about the fact is, whenever you go for custom electrodes, honestly, you'll always be disappointed on the quality. Manufacturing is not just something that comes. We've really built up our manufacturing to make these electrodes really reproducible. So your biggest disappointment will actually be reproducibility. I say 2 problems, I should have said 3. Reproducibility is going to be the biggest issue. You will find people who will do it for you. You can send a sketch to ZP, ZP can do it for you. But when you're having a very bespoke electrode system, unless it's, so for example, we make sure we're manufacturing every day, 5 days a week, because we want to keep the manufacturing constantly going so that everyone's always fresh, the materials are always fresh, the machine's always in use, the machine's always calibrated. Whenever you have a bespoke piece made, it's like batch manufacturing. They make it, everything shuts down, you may come back one day, when they make it again, it'll be very different. So reproducibility is my concern. Cost is a concern. Platinum is expensive. Whenever you can make an assay work on carbon, always choose carbon. Size is a concern here. 40 millimeters by 10 millimeters will impact cost, and quality is linked to reproducibility earlier on. So question number 1, the reason I think you've got the extra peaks is because you're in ammonium acetate. When we were doing our work, we were in something that was kind of much more like tap water, because that was the challenge that we were trying to face. Question number 2, yes, your part is feasible. I'm concerned about reproducibility. I'm concerned about cost. I'm concerned about the materials because they're expensive. I would say send us a sketch, but in the first answer to your question is it's feasible. Question number 3, making a wearable sensor for cortisol. We are doing it. It is implanted, it is in fish, but that has taken us several million euros to do. We're not ready to do it in humans unless there is some funding in place. If you came back to us and started talking about, measuring testosterone in saliva, we could have a slightly different conversation about that. Because it is always easier to do point of care testing or just discrete testing rather than continuous testing. Question number 4, glucose, lactate, sodium, potassium, oxygen, and pH. They love liquid samples. If you come up, for every liquid sample, there's still some development work. So if it's going to be blood, we have to calibrate them for blood. If it's going to be urine, we have to calibrate them for urine. And if you want to roll out quickly, then the SensiAll platform is definitely the platform for you. And then lastly, custom screen printed electrodes. The 40mm by 10mm is a little large. The choice of platinum is going to make it expensive. And even send me a sketch. But even if you don't want to work with ZP, it's fine. You'll also find that I think one of your biggest problems will be reproducibility from the manufacturers, because it's a bespoke piece. It won't have, to get to reproducibility for us, it's, we've taken a long time investing, and then we get to reproducibility. When you've got a new piece, what you get is what you get. And then the next time it gets a bit better, the next time it gets a bit better, and the next time it gets a bit better. But manufacturing doesn't just come on the first, let's say, run. So I think in summary, I'm going to say thank you. I appreciate that was extremely long. My apologies for that. But if you've got any questions of ZP, you can see one thing about ZP is, if you ask us a question, we will try to make a good job of answering the question. So, okay, thanks very much. I do appreciate people who've watched this, and I appreciate we always record so you don't have to watch live. Okay, thanks so much.